So if people have questions, they can ask it in the chat. And I request everyone to mute themselves, otherwise there's disturbance. Okay, please go ahead.
Okay, so I will give an introductory lecture explaining what are Gaussian fields, why they are an interesting object, and what kind of things do we want to know about them. So let me start with some history. So actually, Gaussian fields were used to model various things in nature. So there is this famous paper from 50s where people used them to model ocean waves, and that's another one. So this is actually a good example related to what we are going to study. So this is a photo of an ocean, and what you see, these bright spots are places where you can see sun reflection. So they're actually parts of the water surface that are at given angle. And you can count the density of these points just by looking at intensity on this photo. On the other hand, if you have a Gaussian model, then this is something that is computable, so you can match and see whether your model is a good model, because we have something which is easy to measure and easy to evaluate in your model. Also, say in cosmic microwave background, so the main component of this is Gaussian, and again, you can study geometry of this picture and geometry of the corresponding Gaussian model and compare them. Another reason why I was initially interested in Gaussian fields is this picture. So on the left, we have, so black and white are places where an eigenfunction, high energy eigenfunction of Laplacian is positive and negative. And on the right, there is a certain Gaussian field. I will describe this field later on, but it's, well, it's not obvious what does it really mean mathematically, but when you look at these two pictures, I think it's very easy to see that they are kind of the same type of picture. And an interesting thing is that what you see on the left basically does not depend on what kind of domain do you have. So essentially, if you take any domain and you take eigenfunction of Laplacian with very high energy, this is a picture that you will see. So it seems that Gaussian, there is a certain Gaussian field which is called random plane wave, which describes generic behavior of Laplace eigenfunctions. Now, what are Gaussian fields? There are kind of two ways to think about them. So one way is analytic. So basically, you take any collection of functions that are linearly independent and declare them to be orthonormal bases in some Hilbert space. Or alternatively, you start with a Hilbert space and you take orthonormal bases. And then you look at these kind of random linear combinations. So you sum your functions with independent Gaussian coefficients. Then clearly at every point you will get something which is Gaussian. Alternatively, if say you are a probabilist, then most probably you think of a Gaussian field as a collection of random variables, well, jointly Gaussian random variables that are indexed by a point x. Then, of course, well, sorry, I should have mentioned this before, but in this talk, all Gaussian fields are centered. So I assume that mean value is always 0. And if you have a collection of Gaussian variables like this, then they are completely determined by their covariance function, k of x and y, which is just, sorry, instead of psi, it should be f. So it's just covariance of f of x and f of y. Now, how these two descriptions are related? Well, k can be easily expressed in terms of this orthonormal basis, but the other direction is less obvious. So if I give you k of x and y, it's not quite clear what is the corresponding Hilbert space and what are these eigenfunctions. Now let me give you some examples. So probably one of the best studied Gaussian fields is something which is called Gaussian free field. In this case, the corresponding Hilbert space is the Sobolev space H1, and then the covariance kernel is green function. Now, important thing is, if you go back to this definition, then you can, well, it's actually easy to see that this series will not converge in Hilbert space. It might converge in some other sense, but not in Hilbert space. And this is, and in a case of Gaussian free field, what you get is actually, it's not a function at all. It's a random distribution. And this is not what we are interested in. Now, this is something that we're interested in. So here we take our Hilbert space as something which is called Bargmann-Fock space, and it appears for a lot of reasons in different areas of mathematics and physics. I'm not going to talk too much about it, but one way to describe it is to say that so these functions with the two indices, they form an orthonormal basis. So this uniquely describes Hilbert space and its inner product, and also it describes our field. And then covariance kernel is just Gaussian. So it's a very nice covariance kernel. It has several nice properties that will be important later on. In particular, it's positive. It depends only on distance between x and y, and also it decays extremely fast. So when x and y are far away from each other, this kernel is essentially zero. So this is our ultimate example of the best field. Okay. And then another example, this is the field that I mentioned before. This is something which is called random plane wave. And in terms of, so this is description in terms of covariance kernel. So covariance kernel is just zeroth Bessel function of the distance. And eigenfunction, well, corresponding, sorry, orthonormal basis functions, they're given by these formulas, and the Hilbert space is the following thing. So you take L2 space of functions in R2 with respect to measure which is normalized arc length on the unit circle. So this is a very singular measure. So it's one-dimensional measures living in two-dimensional space. And then you take inverse Fourier transform of this L2 space. And so these functions, sines and cosines times Bessel functions, they are well, they are Fourier transforms of z to the n that form natural basis in L2. Okay, so this is our another important example. Okay, now we are mostly interested in stationary Gaussian fields. They are Gaussian fields such that covariance kernel depends only on x minus y. And then for this type of, so k is a positive definite function, and there is Bochner's theorem, which tells us that any positive definite function is a Fourier transform of a positive measure. And since it's real, this measure is symmetric. So this is something that is called spectral measure. And now we have several objects. So we have our field F, we have Hilbert space, we have covariance kernel, and we have spectral measure. And if you know one, then you know all of the others. And sometimes properties are easier to describe in terms of, say, spectral measure. Sometimes they're easier to describe in terms of covariance kernel and so on. There are some simple connections. In particular, if K is smooth, then F is smooth. And corresponding thing is that spectral measure has finite moments. Okay. Now, what kind of questions do we ask? So first of all, we are interested in large-scale geometry. And most of large-scale geometry can be described in terms of either level sets. So it means that you fix a level, and then you look at set of points where f is equal to L. So our function is a real function of two variables. So level set is kind of generically looks like a collection of curves. Or excursion sets, they're sets where function is above a certain level. And then what kind of questions you can ask, like what is the length of a curve, what is area, how many components, what can we say about topological properties, and so on. So these are observables. And of course, given a random function, for example, length of a level set is a random variable. And then given a random variable, there is kind of a standard trinity of basic questions. So first, you compute expected value, then you compute or estimate variance, and next you would like to prove central limit theorem. Well, and if it's not central, well, sometimes it's not central limit theorem, but some kind of limit theorem. Now, some of these observables are local. And well, there is an old technique started by Kac and Rice. So if you have a function, let's assume that f is just a deterministic nice function. Then there is an easy way to give an integral formula, which gives you number of zeros. So if you have a zero, and then you look at the set where function has modulus less than epsilon, then roughly speaking, the length of this interval is something like 2 epsilon divided by f prime. Which means that if you look at this integral, then it's, well, more or less, it's 2 epsilon times number of roots. So if you rescale it by 2 epsilon, pass to the limit, you get number of zeros. Now, if you have now a random function and you want to compute, for example, expected number of zeros, then you just take expectation, pass to the limit, and what you need is integral of expected value of f prime conditioned on f being 0. And now this is the main reason why we look at Gaussian fields. So if f is a Gaussian function, then this conditional expectation is not that hard to compute. So the same formula is true even if f is not Gaussian. But if f is Gaussian, then this is something which can be explicitly written in terms of covariance kernel K. So it makes computations easy. And this means that things like, I know, length of a level line, area of an excursion set, or Euler characteristic, these are things that can be written in terms of certain integrals, and they can be computed by Kac-Rice formulas. So although these Kac-Rice computations could be horribly complicated, Manju, you're absolutely right. Yeah, there is missing density. Thank you. These formulas could be horribly complicated, but it's technical issue, not a principal issue. So, but when it comes to non-local things, then unfortunately there are no integral formulas, and you cannot use Kac-Rice formulas anymore. And a typical example of a non-local quantity is, for example, number of connected components. So for example, if you know that your field is, say, positive here and positive here, then you don't know whether they're kind of in the same connected components or not. So we lose our standard technical tool. So for a very long time, virtually nothing was known about number of connected components. And then there was a big breakthrough 10 years ago when Nazarov and Sodin proved that under some mild regularity conditions, so you have to assume that your field is smooth, you assume some non-degeneracy, you assume ergodicity, stationarity, and then if you take a fixed domain and now you rescale it by factor R, and you look at number of connected components in this big domain, you rescale it by volume, send R to infinity, then this random variable converges. So remember that N is a random variable. So this random variable converges to a constant both in mean and in probability. So this is kind of a very nice result. And then this result was generalized. If instead of number of components, you look at, for example, number of components with I know, given perimeter, or with given area, or with given topological type, well, basically, whatever you want, same result is true. And another big contribution was done by two physicists, Bogomolny and Schmidt. So they were interested in this Beres conjecture. So they were mostly interested in random plane wave. And they proposed the following argument, that on average, nodal lines, they look like a square lattice. So these kind of lines are like average representation of nodal lines. But nodal lines cannot intersect. So these intersections should be resolved one way or another. And so you create these kind of pictures. And as I will explain in a moment, these type of pictures, they are really a percolation model on square lattice. And for percolation on square lattice, some things could be computed explicitly. In particular, number of percolation clusters is just area times some explicit constant. And if you are interested in variance, then, well, what is the constant is a tricky question, but at least order is quite easy to compute, and it's also r squared. So in particular, it means that number if you believe in this argument, it means that number of domains scale as area, which is a very natural thing, but also variance scales as area, which means that number of domains is well concentrated. So variance is of kind of small order. Now, let me just briefly explain about bond percolation. So we take square lattice, say blue one, and then there is a dual black lattice. And so for each blue bond, there is a corresponding black bond. And then you toss a fair coin, and with probability 1/2, you keep either black or blue. Then you get these black connected clusters and blue connected clusters. And then there are these curves that separate blue clusters from black clusters. And they are kind of a model for our nodal domains. And moreover, Bogomolny and Schmidt suggested that this analogy goes not only for nodal lines and nodal domains, so these are domains when we take level 0, and then corresponding percolation is with probability 1/2. But if you take level which is not 0, what you will get is a percolation model with P which is not 1/2. And here you can see how excursion sets look like for the same functions. So here we have 0 level set and level set 0.1. So these two pictures, they look almost identical, but there are some small changes. So for example, if I highlight the largest white cluster, then on the right, it's much bigger. So when we change level, a lot of things that were disconnected, they are now connected. And this is a typical behavior in percolation. So at critical level, these two things are in balance, and you move a little bit up, and immediately now you have some giant connected components. And well, Bogomolny-Schmidt conjecture, precisely as stated, is probably not really true, but its generalized form is, well, at least I believe it to be true. So what I believe is this, that first of all, Bogomolny-Schmidt conjecture is not about random plane wave. It's about generic Gaussian fields. And in some sense, random plane wave is the worst case scenario. So what I believe, and I call it a generalized Bogomolny-Schmidt conjecture, is the following statement, that if you take a two-dimensional stationary, smooth Gaussian field, and you assume that it's sufficiently symmetric and correlations decay sufficiently fast, then nodal domains have scaling limit, and this scaling limit behaves the same way as critical percolation. Now let me give you a few examples. So a good example, so I can bet that this conjecture is true for this particular field. So if we take Bargmann-Fock field, let me remind you that this is field where covariance kernel is Gaussian. Then for this field, these nodal domains, they have conformally invariant scaling limit, and this scaling limit is the same as what you get in critical percolation. So this is kind of large scale picture. And here I highlighted just one gray domain. And if you have seen large scale percolation picture, it really looks like a large percolation cluster. Now, this is a bad example. So what I do here, I look at white noise on square lattice. So then nodal domains are exactly Bernoulli side percolation with p equal to 1/2. But it's well known that p equal to 1/2 is not critical for side percolation. And what goes wrong here is that this field is not smooth. Now, how can we study all of these? And it turns out that it's really hard to look at one level set, but it's much easier kind of to study what happens to level sets when you move level. And this is kind of Morse theory type of question. So let me explain kind of a Morse theory caricature of what's going on. So we take a field, and let's assume that here we have a local minimum. Then if you take a level which is below critical level, then you get this kind of doubly connected domain. Then as you raise level, this white domain shrinks to a point and then it disappears. So when you cross this level, remember that we look at number of domains above this level. So number of domains does not change, but number of connected components of the level set does change. So here we used to have two boundary components, 1 and 2, then inner component shrinks to a point and then disappears. What happens when we look at local maximum? Well, we have 1, so basically our function looks like this. Then here we have this component. Then when you raise level, it shrinks. Then it becomes the single point, and then it disappears. So when you cross local maximum, one connected component disappears. Now, what happens when you cross a saddle? Well, actually, there are two possible scenarios. One scenario which we call lower connected saddle, and another is called upper connected saddle. So this is one scenario. So you have one domain, and then as you approach critical level, here kind of this place becomes kind of more and more narrow, and then you get this critical point, and now it's disconnected. So you used to have one excursion set with one boundary component, and then it becomes two domains with two boundary components. Alternatively, you have picture like this, then you disconnect things here, but these two kind of things are still connected somewhere else. And this is what we called upper connected saddle. So in this case, what happens is that number of components, number of excursion sets does not change, but number of level sets does change. So here we used to have two boundary components, and now we have only one. And using these type of arguments, we could prove the following theorem. So if we look at, so there are these quantities that sometimes are called Nazarov-Sodin constant, but there are two of them. One counts basically how many excursion sets do we have. So this ES stands for excursion set, and how many level sets do we have. So this is expected number of excursion or level sets per unit volume. And then how you can, now we can describe them in terms of critical densities of critical points. So when we start with our level and raise level to infinity, at infinity there are, well, if you take a fixed domain and take very large, very high level, then there will be no domains at all. So at infinity, basically C is 0. And then you just count. So when you raise level, each time you cross local maximum, you kill one domain. And when you cross lowest saddle, you add one domain. And at the end, you end up with 0. So you get this nice integral formula. Now, what is good about these formulas? Well, critical points are local things. So for them, we could use Kac-Rice formulas. So in particular, density of local minima and local maxima could be just explicitly computed using Kac-Rice formulas. Unfortunately, densities of lower and upper connected saddles are not really local, because you have to know kind of, there is no way to locally figure out whether you get kind of this type of picture or this type of picture by looking locally at a saddle. So locally, all saddles look the same. So it's not really a local thing, but at least it's related to something which is local. And so at least we get this integral representation of densities, and in particular, it implies that densities are continuous, and these densities look kind of like this. So excursion sets for basically any field, excursion set look like this. So it increases, then there is maximum, and then it decreases. So it's unimodal. And then for level sets, picture is a bit more complicated. It could do different things. So for example, for Bargmann Fock, we believe that, well, it's kind of this type of thing. And for random plane wave, well, we know that there are kind of two local maxima and there is local minimum, but maybe there are, maybe picture is more complicated, but we believe that it looks like this. Then with a little bit more work, if you kind of look at this formula, then actually it suggests that these functionals C, they are differentiable, and their derivatives are given by densities of critical points. And again, kind of, if we assume certain things about the field, now we have to assume more. So basically, it's a condition on, so one arm exponent is a condition on probability that there is a very large excursion set. So you look at, say, excursion set containing the origin. And then this controls probability that connected component containing 0 is large. And also, we assume that spectral density is well behaving near the origin. So this is kind of an interesting condition. So for example, it's a condition that is not quite, well, it's not quite obvious what does it mean in terms of covariance kernel. And then under these assumptions, you can say something about kind of how all saddles split into lower connected saddles and upper connected saddles. So, sorry, let me mention just one more thing. So there is another possibility that picture looks like this. So they go to infinity. So this is what we call 4-arm saddle, but basically these 4-arm saddles, they, under some assumptions, these 4-arm saddles never happen. So sometimes it's really hard to verify these assumptions, but actually they are not that bad, and it's easy to check that they hold for Bargmann-Fogg field. Unfortunately, they do not hold for random plane wave, because random plane wave, remember that its spectral measure is sitting on the unit circles, so it has no density near 0 at all. But we have another theorem that under some other set of conditions, and now other kind of assumptions, they, well, we know that they hold for random plane wave. So we can say that differentiability of this C is equivalent to the statement that exactly that this 4-arm thing does not happen. We believe that this is true at all levels, but it's, well, we don't know how to prove it. Okay, and then we can leverage this type of arguments and say something about, yes, there was a question about smoothness. Yes, so we always assume that our fields are sufficiently smooth. Well, at least we want them to be smooth enough so that level sets their nice smooth curves, and in reality we assume a bit more. And yes, so they're smooth enough so that Morse theory could be applied. But I also want to mention that this is a non-trivial bit of Morse theory, because we have to work in domains with boundaries. So this is kind of Morse theory on compact manifolds with boundary and sometimes with corners, which make it complicated. Okay, now this is what Stephen will talk about in more details. So using this kind of Morse theory type of arguments and our previous results about smoothness, we can prove the following results: that for generic fields, so if we assume that field is sufficiently regular, correlations decay sufficiently fast, spectral density at 0 does not vanish, and we assume that this functional CES has non-zero derivative at level L. then variance of number of excursion sets is in ball of radius r is of order at least r squared. And we believe that actually it is of order r squared. Currently, we're working on proving the corresponding upper bound. And the same for level sets. If the corresponding CLS has non-zero derivative, then variance of number of level sets is of order at least r squared. And important thing is that our assumptions hold for Bargmann-Fogg, but not for random plane wave. And another thing is that for any field, CLS is an even function, so its derivative at 0 is 0. So it means that our result is never applicable for nodal lines. It can be applicable, well, it might be applicable to nodal domains, but never to nodal lines. And finally, let me mention about random plane wave, which is another important example. As I mentioned, our result is not, well, our first result is not applicable. And it turns out that actually random plane waves behave differently. So for random plane waves at non-zero level, and if derivative at this level is not 0, then variance is of order at least r cubed. And we believe this to be the right order. Sorry, about one arm exponent. Well, in some cases, yes, it is possible to check positivity. Yeah, so, but for random plane wave, we don't know yet. Okay, and finally, let me mention that recently there was a complementary result of Nazarov and Sodin. So they used completely different approach. So they tried to justify Bogomolny-Schmidt argument. So their argument works exactly for nodal lines. And they prove that for under very, very mild assumptions, their assumptions are much milder than ours. They can show that variance behaves, well, there is a lower bound, there is a polynomial lower bound. So yeah, kind of it's complementary because they get weaker estimate, but much more, well, but their assumptions are much weaker, and also they work with the nodal domains, and we mostly work with generic levels. And I think I should stop now. Thank you. So are there any further questions? Yes, so random plane wave has polynomial decay of correlations. So covariance kernel is a Bessel function which decays like 1 over square root. So the last theorem of Nazarov and Sodin is applicable to random plane wave.
One question. So in the previous, can you go to the previous slide? So this kind of condition that so are there conditions under which you know this unimodality and that this derivative doesn't vanish except at the origin or such things? Or?
Well, so first of all, we believe that there are very few of these exceptional levels. Well, basically, we believe that kind of these are essentially the only two possible scenarios. So you either have one bad point or three bad points. We don't know how to prove it. So even for random plane wave, well, for random plane wave, we know that there are at least three exceptional levels. We don't know how to prove that there are, well, we don't even know that there are finitely many. So we don't know how to exclude these. But for excursion sets, yeah, there is only one exceptional level.
Manju, I'll talk a little bit about how we can prove it in the tails. So if L is sufficiently large, we can prove the derivative is, we can prove monotonicity. I'll mention that a little bit.
Okay. Yes, I see.
Yeah, so basically for high level, there are very few saddles compared to maximum. Yeah, so yeah, it's possible to say something. But extremely high levels are usually not very interesting. So interesting things happen kind of at moderate levels. So at the end of the day, kind of when you talk about very high level, you are talking kind of about large deviations. And large deviations are usually easier than what happens in the bulk. Because you see, when you take extremely high level, which is much higher than variance of your field, then there are extremely few domains.
Yes. In fact, there are asymptotically correct formulas for CES of L, right? As L goes to infinity. So
yeah, so you can get some asymptotic formulas, yeah. So things are much easier at kind of when you look at asymptotic behavior at large levels. But this is kind of difference between large deviations and what happens in the bulk of your distribution. Okay. Any other questions?
Any other questions?
I have one question. So the formula you had for number of components or so, is this kind of generalized to other Betti numbers or other homological thing?
It should be. It's just, so I'm pretty certain that if you move to higher dimensions, something like this should be true, because after all, Morse, well, it's Morse theory, and Morse theory works in kind of higher dimensions, and well, you just have, well, the problem is that not only you have more types of critical points, you see, kind of, we also have to split saddles into these up and lower connected saddles, like this. And when you move to higher dimensions, well, more complicated things could happen.
Yes.
So probably if you introduce kind of other, well, basically, well, it's about connectivity types. But I'm not sure that it will be possible to analyze these things. Because, well, they will be just more complicated.